Hi folks, welcome to part 2 of Unit 3, Lesson 2. Okay, so we're going to take up these questions here that hopefully you've worked on. So it asks us to determine the local extrema for the following functions algebraically, and we'll check our answers. And the first one here is just a quadratic. Now, of course, you already have methods for doing this. You could complete the square. You could find the x-intercepts, if there are any, and then average them out to find the x value of the vertex. But we're going to see now that with calculus, we can do this much, much quicker. Okay, so let's remember our first derivative test here. We find our derivative, find the x that make it equal to 0 or not exist, test the sign of the intervals. If it changes sign, depending on how it changes sign, we'll have a local max or min. And of course, we're only interested in points where the function actually exists. So no need to worry with any points on a parabola. They all exist. So let's start by finding the derivative. Okay, and we have 2x minus 10, and we want to set this equal to 0. So 2x equals 10, x is equal to 5. Okay, and so all I have to do is determine whether the derivative changes sign at 5. And again, it has a positive slope, so we know that this is a line that goes this way, increasing, so it's going from negative to positive. All right, so let's remember what that means. And if instead of memorizing it just in your head or with your pen, say this means it's going from decreasing to increasing. In other words, we have a local min. All right, which makes perfect sense because it's a parabola with a positive leading coefficient, so we know that it should have a vertex and that it indicates that it's opening upwards. So in other words, has a local min. Now, if they're actually asking for the local extrema, what you should be doing now is taking this value, putting it into the original function to find the maximum, in this case here, the minimum y value. I'm not going to do that. You can do that yourselves. Okay, I'm just going to go through the process of determining where the extrema occur. All right, so you take a look at the next question. Again, x squared e to the x. This will have a domain of all real numbers. So let's see if it has any local extrema. So step 1 is to take the derivative. Okay, we're going to have to use a product rule. So the first is 2x times the second function e to the x plus x squared, first function, times the derivative of the second, which of course is just e to the x. And again, we want to set this to 0. We don't have to worry about where it doesn't exist. What do we do here? Hey, just factor out an e to the x, and in fact, they also have a common factor of x. So I'm going to factor out an x e to the x, and we see that we're left with just a factor of 2 in the first, plus a factor of x in the second, and we see just how easy using that trick makes solving this equation. All right, so that means that x can be equal to 0, e to the x can never be equal to 0, so we don't have to worry about that one. And if we solve this being equal to 0, x is negative 2. All right, so let's find our signs. Okay, so we have negative 2 and we have 0. So let's pick negative 3. And I'm going to put this into the factored form. So remember, e to the x is always positive. I never have to worry about it. So this is going to be negative, and then 2 plus negative 3, negative. So negative times negative is going to be positive. Okay, let's pick negative 1, negative, positive, and 2 minus 1 is also positive. So negative times 2 positives is going to be negative. And let's pick, say, 1, positive, positive, positive. All right, so what does that tell us? Here, from positive to negative, meaning from increasing to decreasing. So here we have a local max, and here I'm going from decreasing to increasing. So here we have a local min. And again, if I wanted the actual y values, I would just stick those into the original function. Okay, and we'll check these on Desmos later on. Okay, although it's looking pretty good so far. Now this one here, now you certainly can use the quotient rule to find this derivative, but I hope you saw that you could actually distribute out this division by x. So I can actually write this as 1 over x, so x to the negative 1, minus x squared over x is just equal to x. A lot easier to find the derivative. So y prime, okay, derivative of the first is just negative 1 times x to the negative 2, minus, and the derivative of x is just equal to 1. So again, I want the derivative to be equal to 0. So this is negative 1 over x squared minus 1. Okay, multiply both sides by x squared. So this still remains 0. And I just have negative 1 minus x squared. But when I try to solve this, I get x squared equals negative 1. All right. So this has no solution. So the only place where the sign could change would be at 0, okay, which makes the first derivative not exist, okay? But even if the sign does change, this function doesn't exist at 0. So I could still determine the sign of the derivative. That'll tell me whether it's increasing or decreasing on that interval. So that might be useful for me, but I can't have an actual local max or min. So let's just find it just for the fun of it here. So if I take my derivative here and I put in negative 1, okay, I'll put it into this equation here. So negative 1 squared is 1 squared. So I have a negative number minus 1 is still negative. And then if I put positive 1, well, I have 1 over 1 is 1. So negative 1 minus 1, there you go, still negative. Okay, so I expect it to be decreasing on both sides. But, even if it had changed sign, there wouldn't be a local max or min here because the function doesn't exist there. Okay, all right, let's take a look at this last one. And in number 7, they imply to me that there's maybe something of interest in this question beyond just the local maxes and mins. Okay, maybe that'll lead us to what we're doing next time. So start by finding the derivative. So y prime is equal to 4x cubed minus 3 times 6 is 18x squared plus 2 times 12 is 24x. Okay, and I'm going to set this to 0. So let's start by factoring out. Well, I can definitely factor out a 2x. Okay, so what are we left with? We're left with 2x squared minus 9x plus 24. So definitely x can be equal to 0. So if I look at this here, I have to get to an odd number. So, sorry, this should be 12. Sorry, I took out a factor of 2. Okay, this is why always taking a second look at your algebra before you move on is not a bad idea. So here, even if I try 3 and 4, 2 times 4 is 8, and 3, I don't think I'm going to be able to factor this. So let's use the quadratic formula. So x can also be equal to negative b. So 9 plus or minus the square root of negative 9 squared. So 81 minus 4 times 2 times 12. And before I move on, I see that, this is 48 times 2, 96. This is going to be negative. So this provides no x-intercepts for the derivative. So the only time that it can change sign is at x equals 0. Okay, so let's see if there is a change in sign. All right, so let's stick in negative 1. Well, here, if I stick in negative 1, in fact, I think this is going to be always positive or always negative since there's no x-intercepts. So let's just check negative 1, 2 times negative 1 squared. So that's 2. Okay, minus 9 is negative 7 plus 12, so positive. Okay, times, and here when x is negative, so positive, negative. There we go. Looks good. Now let's stick in x equals 1. So again, 2, sorry, actually that should have been 2 plus 9 because I was putting negative 1. In the end, this still turns out to be positive. Okay, just made a little mistake, but didn't change the end result. If I put in positive 1, 2 minus 9 is negative 7 plus 12, still positive, times now x is positive because it's 1, so that's going to be positive. So I should have so again, decreasing to increasing, I should have a local min here. All right, so let's keep in mind what we have. Local min for the first one, a max followed by a min, nothing, no local max or min at all, and then a local min. So let's take a look at these graphs, and we'll spend some time looking at that last one. Okay, so let's see, what do we have? We have our parabola. There you go, not surprising at all. Local min and that was at x equals 5. All right, and again, if we take the derivative, we see it was that line, it crosses the x-axis. Okay, let's take a look at x squared e to the x, okay, and its derivative, and we see that, yeah, at -2, we have a max, derivative goes from positive to negative, and at 0, we have a min, and the derivative goes from negative to positive. So all good, okay. Now this one here isn't supposed to have any maxes or mins, and if we look at it and we see, well, that's right, no maxes or mins, right? Let's take a look at the derivative, okay? Now, notice here, we did find that derivative should have been negative on either side, which tells us that the function is decreasing on this interval and still decreasing on the other side of 0, okay? So this derivative is giving us a lot of information. And now let's take a look at this last one. So here we found only one local min. And when we draw it, okay, well, a bit tough to see. I think I'm going to change this a little, but definitely only one local min. And we see that the function only has an x-intercept at 0 and it crosses through. But let's change this a little here. So I think we don't need much. I think I'm just going to go from like maybe -2 to, I don't think I'm going to go more than 4 here. Okay, and then let's maybe even, I think this is good enough. Okay, now it's a little tough to see, but I want you to take a look at what's going on with the function here. I notice that the function, okay, the derivatives are getting steeper and steeper. And if you notice here, there's a bit of a squiggle. Let's see if we can maybe change this a little more. Let's maybe put this to, 25. Okay, again, a little tough to see, but if you notice here, the derivatives kind of get steeper, and right here there's a little hump. They start to get less steep for a while, and then at some point they start to get steeper again. Okay, so a little tough to see, but there is a bit of a squiggle here. Now, kind of interesting, because they seem to be getting steeper up until this point, where the derivative, okay, stops increasing, and then they get less steep, derivative goes down, and then eventually at around this point they start getting steeper again. Now I don't think this should be too surprising because we've seen this kind of behavior before, but it looks as though something interesting happens with the original function when the derivative has a local max and a local min. And of course, what tells us where the derivative has a local max and a local min? Well, where the second derivative, in this case here, looks like is going to be equal to 0. So it looks as though the second derivative might actually come into play to help us give us information about that original function. Okay, but that'll be for the next unit. That's it for this one.